Good evening all of you. So, I welcome you all to this FDP on optimization of ML algorithms. I am going to talk about one of the popular optimization algorithms, optimization technique in ML algorithms mathematically. We are going to solve problems numerically with pen and paper and try to understand how the algorithm works. Also, we are going to explore the implementation of the algorithm or the optimization technique in Python programming. So today we are going to discuss about in general what is optimization, and then the gradient descent technique, different variations in gradient descent, a small demo in Python programming. We will see how to how do we actually do this, because whatever we do in mathematically can also be done programmatically, which is very quick and fast, and then we will come to a conclusion. So what is optimization? Why do we have to actually optimize ML algorithms? The best example, when you have a regression model based on some data, right? You have some data set with you. With that data set, you have formed a model. Let's say I formed a regression equation y equal to mx plus c, or in general I will say with some example I will say 3.5x plus 4. If I have a regression model like this, y equal to 3.5x plus 4, how did I get this model? I got this model using the historical data. Right? Now, when I am actually doing the testing of this model, means I am giving new data points for this model, right? How accurately is it giving? Is it giving better results, or is there any lot of difference? So, in simple numbers, if we talk, let's say I have some values x1, x2 and y. Right. So, given values of x1, x2, I am finding out the value of y. This we do in regression. So, using some 80% of data, I build a model, and that equation is y equal to 3.5x plus 4. Now, with the remaining 20% data, we will be actually doing the testing of the model. So, while doing testing, I know the values that if x is 10, or let us say only one x here, if x is 10, right. So, the actual value is maybe 40. Okay, but when I substitute this value here, what am I getting? 3.5 into 10 plus 4. So, this is 35 plus 4. Right, it is giving 39. It is giving me 39. So, the actual value is 40, but the value which my model is predicting is 39. So, there is some error in the prediction. Whatever the ML model is doing, predicting, there is some error in that. There is some gap in the actual value and the predicted value. So, when I want to improve the accuracy of the model, what is my model? It is a regression model. It is a regression model, right? Regression, again here you can say as a line equation, mx plus c, right? So, I want to optimize the error value. I want to minimize the error. So, whenever we talk about minimizing or maximizing, it means we are talking about optimization. Optimization means either you minimize values or you maximize the values. Right. So, in the simple example of regression, we have observed that the model which I have got, that is 3.5x plus 4, this is actually not performing well. There is some error in the actual value and the predicted value. The accuracy of this model is poor, not good. So, in such context, let it be any algorithm, let it be logistic regression, let it be k-means clustering, all those algorithms, what they have to what they supposed to be done and what they are actually doing, there might be some difference in that. So, we want to adjust the model parameters. We want to adjust the model parameters such that the error between the actual and the predicted value is very, very low, which can do better predictions. Right. So, adjust means what should I adjust here? See, I want to adjust the value of 3.5, I want to adjust the value of 3.5 and 4. Right. It means I want to find out a new value for that. Let us say 3.52x plus 4.011. See, these values have slightly modified now. 3.5 became 3.52 and 4 became 4.011 to make better predictions. So, I want to adjust, find out new values for M and C such that the error is very less. So, this is optimization. Any ML algorithm you talk about, in those algorithms you have the model with you, that model is doing predictions, it may not be doing up to the mark. So, you have to adjust the parameters such that they do better predictions, right. So, what they do, these algorithms help models learn from the data by finding the best possible solution through iterative updates. So, there are generally two types of optimizations, two types of optimization algorithms. One is first order algorithms, then the second order algorithms. Okay. So, what are these first order and second order algorithms? First order algorithms. The first order optimization algorithms are methods that rely on the first order derivative. So, if you have a function f of x equal to x cube, what is its first order derivative? F dash of x, it is 3x square, right. So, there are some algorithms which only depend on the first derivative, that is first order derivative gradient. Okay, first order derivative of the objective function to find the minimum or the maximum. Those kind of algorithms are called first order algorithms. If I do f double dash of x, what is the value here? 6x. This is called second order derivative. So, algorithms which only depend on the first order derivative, those kind of algorithms come under this thing, first order algorithms, right. So, they are very simple to use and very efficient. Some of the examples of first order algorithms are the gradient descent, stochastic optimization, evolutionary algorithms, right, meta heuristic algorithms, swarm intelligence algorithms, and so on. There are a lot of optimization techniques which are based on the first order gradient, right. What are the second order algorithms? They use both first order as well as the second order, the gradient as well as the Hessian. They depend on both of these parameters, right. So, what are some examples of that? Newton's method, I think quasi-Newton method is very popular in deep learning, or we use this. Constraint optimization, Lagrange multiplier, these are some algorithms. Then we have Bayesian optimization. They use both first order derivative as well as the second order derivative, right. So, we are going to focus on the first order algorithms in this FDP, and especially we are going to look on the gradient descent technique, right. So, let us understand what is gradient descent. It is one of the method for optimizing, or I would say unconstrained mathematical optimization. There are no constraints in this. Generally, optimization means we have lot of constraints. Any classical mathematical problems, if you see optimization problem, we have lot of constraints given, right. So, in operation research, we have this transportation problem, assignment problem, we have lot of constraints given. They are also optimization problems, but depending on some constraints. But this gradient descent is an unconstrained optimization technique, and it is a first order derivative. What it does? The idea is to take repeated steps in the opposite direction of gradient. Okay. So, before I explain the technical parts of this, let me demonstrate this with a simple analogy, right. This is a very popular example to explain gradient descent. Okay. What is this? Suppose you are on the top of the hill, let us say you are here on the top of the hill, and there is full of fog, and you cannot see the downhill, you cannot see that, right. People are stuck in the mountains and they are trying to get down. They are on the top of the mountain, they want to come down. There is heavy fog such that the visibility is very low. Okay, something like this. There is a heavy fog and visibility is low. Now, how do we go down? If I take a wrong step, I may fall down. There might be a steep and I may roll down, and I may come down in maybe in some lake I may fall, or some I may go into some other caves. I don't know where I will fall into. I want to come down off the hill safely, right. So, therefore, the path down the mountain is not visible. So, they must use local information to find the minimum. What they do? They adopt the technique of gradient descent. What is that technique? What they do there, right? So, the technique is Wherever you are standing, from there you use a small stick. With that stick you just click here. I think you might have seen some blind people on the roads, they keep hitting the roads to see is there some object or some drainage is there or some canal is there, they keep hitting the ground. Same way, like this, you have to from that place wherever you are, you have to look around for place where there is some land. You have to click like this. See, using that you reach this position. Again from there you apply the same technique, somehow you will be reaching your destination. So what this technique they do, right? They eventually find their own way, right, by finding the local minima. So what they do here, see, from standing here, from this point I am using a stick. With that stick I am seeing how long there is land, then I am moving to that place. Again from there, again I am using the same stick, looking where there is land, again I am moving forward. Like this, step by step we reach the destination. So in this small scenario of that climbing down the mountain or the hill, right, indirectly it uses the technique of gradient descent. Why? You see here, the people represent the algorithm. How does the algorithm works? That is, the people represent the algorithm. The path they take represents the parameters. The steepness of the hill represents the slope of the function of that point. So when you are here, when you are using stick and looking the how much steep that hill is from there, that is your slope. The instrument which you are using for measuring is your differentiation. The stick which you are using is the differentiation, right? The direction which you are choosing is aligned with the gradient of the function. Okay, whichever direction you are moving towards, that is depending on the gradient. The amount of time they travel before taking another measurement is the step size, right? So I think you understand now, or this with this simple example, or the another best example to explain gradient descent will be, you are asking your friends, let's say you wrote exam of 100 marks. Okay, there are two friends A and B. A is asking B that guess my marks. A is asking B to guess the marks scored by A. So then B is telling maybe you got 70. Then A tells no, it is not that low, it is better only. Then he will tell 90. Then again A will tell no, 90 is too high. Then B will tell 80. Then A will tell you are closer but not exact. Then again maybe B will tell some 78. Then again A will tell yeah, you are almost reached, but it is not true. Then he will make another guess, some 77 or maybe 79. Like this, by making different guesses, in maybe some 10 guesses, you are able to find out the exact marks which A has got. Okay, so this we generally do know. You can ask your friend, guess it, again guess, you are near, you are close. This way we keep doing it. So between different values, somehow you will reach to a actual point. So this is the logic of gradient descent. You are making a guess. Now when you are making a guess, what was initial, how much did you increase? 20 marks. Then you reduced 10. Again you reduced 2. Then again 1. Then again 0.5. Like this, you are reducing the value, marks value, and you are reaching to the destination. This is the logic of gradient descent. What gradient descent does? Let's try to understand. Right? The idea is to take repeated steps. Repeatedly you do that. From the hill, what I am doing? I am putting my stick. Yeah, I found the land. Move forward. Again from there, use the stick. Again move forward. From there again use the stick. Move forward. That way, repeated steps in the opposite direction of the gradient of the function at the current point. Right? So this is direction of steepest descent when you want to come down. When you want to go maximize it, it is gradient ascent. Right? So this gradient descent is useful in minimizing the cost or the loss function. Okay. So generally it is based on the observation that if the multivariable function f of x is defined and differentiable in a neighborhood of a point A, then f of x decreases fast. Okay. So, it uses this. See, the new value is equal to old value minus the step size, right, step size. That is what you were guessing when your first guess was 70, then he said no, you are going more, then you came 90, he said no, it is more, 90 is more than then using 90 you reduced some 10, you got 80 new value. Again based on his comments you were adding and subtracting and you found out the value. So, gradient descent, the basic idea is to find out the new value based on the old value and step size, new value equal to old value minus step size. So, here mathematically the a n plus 1, the new value is equal to a n minus, see this step size, what is step size, what is the formula for step size, I am telling new value is equal to old value minus or plus step size. What is step size? Step size is learning rate into slope. So, the step size is learning rate into slope. So, this is here the eta represents the learning rate and the slope is represented by the derivative value delta f of a of n. Okay. So, this is the core formula in gradient descent algorithm, right. So, if you see here I am reaching somehow the closest point from x naught, I am moving x1 then x2 x3, I am going towards the actual point where I have to reach, right. So, this is the technique of gradient descent, you make a guess, you find out the new value using old value minus the step size, or step size could be written as learning rate into the derivative of the function, which will give us the direction, right. So, this is the core idea behind gradient descent technique. So, we understood this approach. What is the cost function here? Now, which one should I optimize? So, we have to optimize a cost function. So, in this example of regression which I explained here, we have seen that when I have a model 3.5 x plus 4, I have to optimize the value of m and c. I have to optimize the value of m and c, right. So, how do I optimize this m and c, right. So, for that what is the we have to define a cost function. So, for my regression example, the cost function could be mean square error, it could be mean square error, we can take any function, right. So, we need a cost function definitely, that cost function we have to optimize it. So, if it is a function that measures the performance of a model, cost function quantifies the error between the predicted values and the expected values. That is what we have to reduce actually. When I am doing a predicted value, this is my actual value and my predicted value, I have to find out the reduce the difference between both of them, actual value minus predicted value. I have to reduce this error, right. So, there are a lot of cost functions, one could be mean squared error. Okay. So, by making after making a hypothesis with initial parameters, we calculate the cost function, right. So, now if you see here for a simple linear regression, what is my hypothesis? My hypothesis y is equal to, again in mathematically we write here h of x is equal to theta 1 x plus theta naught. Okay. So, I have to optimize the values of theta naught and theta 1. So, those are my parameters, theta naught and theta 1 I have to optimize. What is my cost function here? I am using here the mean squared error MSE value. So, my cost function is 1 by 2m summation of I equal to 1 to m, right, the actual values h theta of xi minus the predicted values whole square. Now, this I have to optimize. So, what I have to do here? I have to minimize the values of theta naught and theta 1 such that it does the better predictions. Minimize or maximize depending on the problem. Okay. So, this is my cost function, it is very important. So, yeah, gradient descent, it is something like this, right. You compute the gradient first, okay, that is the first order derivative of the function, then make a step in the direction opposite to the gradient. The opposite direction of the slope increases from the current point by alpha times the gradient at that point. Alpha times means the learning rate what we are taking, right. So, this is how the gradient descent technique works. So, we have seen about cost function. What is this learning rate? See, what is the impact of learning rate, right. So, if learning rate, again I will go back to that. See, new value is equal to old value minus alpha into the slope. Okay. So, in this example if you see, right, the steepness of the hill is the represents the slope, right. So, the instrument we are using is the differentiation and the direction I am choosing is the gradient. Amount of time is the step size. So, to find out the time, okay, so how long should what should be my learning rate? How should I learn? Should I reduce 0.5 always, or should I do 1 always? So, when you were guessing your friend's marks, what were you are guessing? First time you made 70, then you made plus 20, 90, then you made it minus 10, 80, then again you reduced minus 2, then again you increased plus 1, then maybe again you have made minus 5, then again plus 0.5, right. So, your learning rate is changing here, your learning rate is changing. So, what should be your learning rate? How should you do that? So, if you have a good learning rate, if you see the loss, right, with the number of epochs increasing, the loss is decreasing, this red line. But if you have very high learning rate, your loss might increase, right. So, you should choose a optimal learning rate value. Okay. If it is too high, it might overshoot. If it is too small, the training might turn out to be too long. Okay. If it is optimal, the model converges to the minimum. So, if it is a good value, it reaches to the minimum, reaches the actual value here, right. So, learning rate is an important parameter. We should be very careful while choosing the learning rate value. Now, step size. This is a simple thing. What should be your step size? How much time should you travel? You have chosen that, how much time you should travel. So, in the mountain example I am talking about. So, step size here. See, if I choose my step size as 0.8, okay, what will happen to this? See, I got a new value now, right. I got a new value here. Next, 2.4, I got a value here like this, 2.4. Initially it was this, from here I have gone here. Next, again if I do it another time, if you see, I am getting minus 1.44. So, from here I went here and then I am coming this side. Okay, I am doing plus minus, I am doing this, right. Next, again if I keep doing that, if I keep doing it like this, I go here, then again come here, come here, come here, I reach that point. Okay, finally I reach at the minimum point here. We know the minimum point for f of x square will be 0 definitely, but am I reaching directly to 0? See, 2.4 minus 1.44, 0.864 minus 0.5, then 0.3. You can observe the values here, right, how the values are fluctuating between from here to again this way, it is fluctuating, right. So, choosing your step size is also important, step size matters. Okay. So, we have seen how the value is changing. After 30 iterations, I got something which is very equivalent to 0, not exactly 0, equivalent to 0. How long should I do this? Until I get value very closer to that. Something value is less than 0.001, or we can define this 0.001, we can define this, right. So, see here, if I choose the step size, how it is iterating from this point, how the different step size it is coming to it is converging to the actual point, right. So, if step size is 0.2, it does it like this, in multiple iterations it converges like this. See, directly from here it is coming to this point, right, here, then from here, then here, then here, it is coming to the actual point, right. So, step size matters. See, sometimes for these kind of line equation, your step size, see, it goes from here to that side and then it comes to the point, or sometimes it may fail also. See, actually it has to come here, but it went there, that side, it found that as the best value. Okay. So, step size also matters in this, right. So, yeah, so this is little about the cost function, the step size, the learning rate, right, all those are the parameters. So, what are the different types of gradient descent algorithms? We have three different types, right. One is batch gradient descent, the stochastic gradient descent and mini batch gradient descent. Let us see each one of them. What is this batch gradient descent? In batch gradient descent, it updates the model parameters using the gradient of entire training set. Okay, you will understand it better once we solve with a numerical problem. If you are choosing the entire training set, then it is called batch gradient descent. It is good to calculate, because within a few iterations we will get the answer, right, but it is very slow for large data sets. It converges to global minimum, but can be computationally expensive and very slow for the large data sets. In batch gradient descent, we choose the complete data set, complete data points, and then we try to find out the gradient of that. Then the second one is stochastic gradient descent. What is the stochastic gradient descent? In this technique, we will choose one training example at a time. We will choose one data point at a time and build our keep repeating the process. This is also computationally, it is very good, computationally efficient. It is also faster, but sometimes it is noisy, because when you have large data sets, you see, you are doing here for one example, one data point, you are doing the iteration. That is not good, right. And the third one and the best one is mini batch. So, you divide the data points into batches, and then when you divide them into batch, you try to find out the values batch wise. In that case, it is better in terms of efficient, it has less noise, and it is in between batch and stochastic. So, mini batch is kind of average model which does better compared to both of them, right. So, these are the three different types of gradient descent algorithms. Okay. So, one is batch, stochastic and mini batch. I will explain this with the help of a numerical example. Let us try to understand this. See, so assume I have given some data x and y. So, I have given 1, 2, 3 and 4. So, this is the data point given to us, right, and I have to choose my cost function. My cost function I am choosing as mean square error. So, it is nothing but 1 by n summation of I equal to 1 to n yi minus the actual value. So, I will write predicted value mxi plus c. This is my cost function, mean square error. I am using mean square error function as my cost function. Okay. So, the data given to me is 1, 2, 3, 4 x and y. Only small example I am taking to demonstrate how gradient descent works. Now, initially, so what is my simple linear regression model? My regression model is m x plus c. So, you have to assume some initial values. What does gradient descent do? It assumes some value. See, when you are on the top of the hill, you are at some point, that point is to be assumed. You are at some point that has to be assumed. So, we will assume m naught equal to let us say 1 and c naught equal to 0. And what is your learning rate? What should be your learning rate? So, I am assuming my learning rate to be let us say 0.001, right. So, using these values, we will try to find out the model. See, now when m naught equal to 1, c naught equal to 0, what is the line equation? What is the regression equation I am getting? Y equal to m naught x plus c naught. So, what does the line equation becomes? It becomes 1 into x plus 0. So, y equal to x is the model. Y equal to x is the model. Now, you go and do the prediction. Is it doing properly? No. When x is 3, y is 4. But this model, you see, y is giving, it is still giving us 3 because x equal to y. If x is 3, y also will be 3. So we have assumed some values, right? We have assumed some values. Now we will try to apply gradient descent here. Okay. So what I have to do? I have to first find out the derivative of this cost function. The approach in gradient descent technique is we have to find out the derivative in the cost function. So what are the two variables? What are the main parameters which I am playing? What is my focus on? My focus is on optimizing the values of m and c. My focus is on optimizing m and c values, right. So for that we have to use our cost function. So what we do here, we try to find out derivative of our cost function. So what we do here, since it is partial derivative, why it is partial derivative? You see, when there is a function of more than one variable, we have to apply partial derivative. This function is a function of two variables m and c. So we have to apply partial derivative. So I will find out dou f, let us say this function is f or cost function j, let us say. So the value which I am finding out is dou j by dou m. With respect to m, if I do derivative of this function, what is the value? See, it is m function of square. So it comes front 2 by n summation of I equal 1 to n. This remains same, yi minus mxi plus c. This remains same into the the m value. So it is minus xi. It is because m becomes 1, c is constant, it becomes 0, y is constant, it becomes 0. So the internal derivative of this is minus xi. So if I write it clearly, it becomes minus 2 by n this function into xi. This is my partial derivative with respect to m. Again, now find out the derivative with respect to c, dou j by dou c. How to find out partial derivative? See, 1 by n summation of, see, this is also again function is square. So 2 comes front. So 2 comes here, 2 by n summation of, this remains same, yi minus mxi plus c, this remains same, into derivative of c is 1. So there is no change. There is no change. Now why you need these values? See, I already have m0 and m1 c0 values. How do I find it? How do I find out the new values m1 and c1? What is the formula for m1? We have already seen this. I think you remember. The formula used in gradient descent is an plus 1 is nothing but an minus alpha into derivative of f of a of n. So I am going to use this here. So m1 is equal to m0 minus alpha into dou j by dou m, right. Then c1 is equal to c0 minus alpha into dou j by dou c. Okay. So this way we have to find out the new m1 and c1 values. So new data point we can find. Okay, let us calculate that. So you see, we have taken here x, y as 1, 2, 3, 4. Substituting this in dou j by dou m and dou j by dou c, we will try to find out the value. So for this, first we have alpha is given, see, m0 is given in the problem, alpha is given in the problem. You are given m0 is equal to 1, you are given alpha equal to 0.001. We have to find out the value of dou j by dou m, and we have to find out dou j by dou c. If I can find out this is my gradient descent equation. If I find out that, I can get my new m1 new values for m and c. Okay, so let's find out dou j by dou m, dou j by dou m. What is derivative? What we got here, derivative, see, minus 2 by n. It is minus 2 by n is 2. Why? There are 2 data points. N is 2 because there are 2 data points. Minus 2 by 2 of, yeah. So yi means 2. So here I will write. I will just write down data points here, x, y, so that it is easy for us, 1, 2, 3, 4. Okay, so yi minus, so 2 minus m See, here it is m xi plus c into xi. Okay, so it is m naught. M naught means 1 into xi, that is this one, plus c naught. C naught is 0, this value into xi, that is 1. I am just substituting it in the dou j by dou m. So what we get here? Here you see this dou j by dou m 2 by 2 goes away, and 2 minus 1 into 1. So this becomes minus 1. It becomes minus 1, right? Dou j by dou m value. No, this is for one data point. Sorry, this is for one data point. We have to do it for multiple data points. No, so this is one case, plus for the second data point. So what is that? 4 minus again m into m naught into xi. M naught value is assumed to be 1. C naught is 0. So m naught 1 into 3 plus c naught 0 into 3. Why is this 3? Because into xi, in the derivative I got it as xi, right? So just calculate this. This 2 and 2 goes away. So this is minus of, you calculate this, 1 into 1 1 plus 0, this is 1, 2 minus 1, it is 1, again 1 into 1. So 1 plus from here 4 minus 3, this is 1 into 3. So 3, 4 minus 3 is 1 into 3 is 3. So it is minus 4. Therefore dou j by dou m at data points is nothing but, dou j by dou m is nothing but minus 4. Now let us go and find out the new value for m1. How to find out new value for new value of m? We know, we already seen the formula here, right? We got dou j by dou m as minus 4. So you substitute the value here, right? M1 is equal to m naught minus alpha into dou j by dou m, right? So what is m naught? 1 minus, what is alpha? 0.001 into minus 4. So this value, if you calculate, it is somewhere around 1.004. This is my new m1 value. Okay, so new m1 value is 1.004. Now let us find out dou j by dou c. Let us compute dou j by dou c. What is the formula I got dou j by dou c here? See, 2 by n summation of yi minus mxi plus c. So it is very straightforward. So 2 by 2 into yi, that is 4, minus 1 into 3 plus 1 into yi is 2, no, 2 minus 1 into 1 plus 0. This is one set, plus another one. See, it is 4 minus 1 into 3 plus 0. This is my actual dou j by dou c. So if you compute, this goes away here, 2 minus 1, it is 1 plus 4 minus 3. 4 minus 3, yeah, this is also minus, sorry, this is also minus, because c value has minus here also, right? So 4 minus 1, it is 1. So this is minus 2. This value is minus 2. So now we have dou j by dou c as minus 2. Using this, what is the new value for C1? What is the new value of C1? Let us find out the new value for C1. Right. So we know C1 is equal to C naught, it is C naught minus alpha into dou j by dou c. So C naught is equal to 0 minus 0.001 into minus 2. So C1 value becomes, if you calculate this, this becomes 0.002. So this is our new C1 value, and this is our new M1 value, right? After one iteration, we have found out the values. So how does gradient descent works? Actually, it is trying to find out the actual values. By assuming some base values, by assuming some initial values, we are trying to repeat the procedure and trying to find out the actual values, right? It keep doing it. So if I just write down what we have got, we have assumed m naught as 1, c naught as 0, and alpha equal to 0.001. What we have got here after first iteration, m1 is 1.004, c1 is 0.002. Now, in the next iteration, you have to repeat the same process. In the next iteration, we have to do the same thing. We have to use these m and c values, m1 and c1, and try to find out m2 and c2, and keep doing this always. Right? Repeat this procedure. How long we have to do that? Until the value of the cost function, is very minimal. Okay, so you have to keep calculating the cost value always. With m and c, what is the cost value? With m1 c1, what is the cost value? With m2 c2, what is the cost value? Keep repeating this continuously till we get different values. We get very less cost value, or the error difference is very low. Right? This way this gradient descent works. Let's try to understand the three different variations. I talked about batch gradient descent, stochastic, and mini batch. What is this? Where is the difference? Let's take a simple example. Let's take, I have some data points 1, 2, 3, 4, 5, 6. Let's say 3 data points are given to us. Right? If you observe in the previous calculation here, when I am trying to find out this dou j by dou m and dou j by dou c, I am using all the data points. Right? We have seen just now how I am using dou j by, when I was calculating dou j by dou c, right, minus 2 by 2, it is 2 minus 1 into 1 plus 0. See, I am using x1, y1, I am using x2, y2. Both the values I am using here. So, whatever data points are given to us, everything we are using. So, this is called batch gradient descent. So, that is what in batch gradient descent. What we do, when you are calculating dou j by dou m and dou j by dou c, right? When you are calculating dou j by dou m and dou j by dou c, we use all the data points. Right? This is batch gradient descent. What is stochastic gradient descent? In stochastic, what you do is see. So, given the same data points 1, 2, 3, 4, 5, 6, right. So, we will guess some value, m naught is 1, c naught equal to 0. Let us say first iteration, what I will do, I will find out m1 equal to m naught minus alpha into dou j by dou m. See, when I am calculating dou j by dou m here, I will use only x1 comma y1, that is 1 comma 2 only. When I am calculating the dou j by dou m, only the first data point. In stochastic gradient descent, we use only the first data point x1, y1. Then we use next, when I am calculating m2, I will use m2 equal to m1 minus alpha into dou j by dou m at 3 comma 4, only second. So, first data point, here I will be using second data point. Right? When I am going for third iteration, m2 minus alpha into dou j by dou m. Here I will use the third data point, that is 5 comma 6. This way, see, in stochastic gradient descent, I am using only one point. First one, then second one, then third one, again first one, again second one, again third one, and so on. Whereas in batch gradient descent, if you see, when I was calculating dou j by dou m, I was using all the values in the data set. Right? Now, the third one, mini batch. So, when the data set is something like this, x, y, you have here values 1, 2, 3, 4 and 5, 6. When the data points are like this 1, 2, 3, 4, 5, 6, you will divide this into batches. You will make batches. So, let us say batch 1, I will put 1, 2 and 3, 4, and then batch 2, I will put only 5 and 6. I will make this as batches. So, what happens here? When you make batches like this, see, B1 contains 1, 2, 3, 4, and B2 second batch contains only 5 comma 6. Now, you see the procedure. We know m1 is equal to m naught minus alpha into dou j by dou c. We know this, dou m, sorry, dou j by dou m. This dou j by dou m you will calculate at B1 points. Then second iteration M2 you will calculate M1 minus alpha into dou j by dou m at batch 2 data points. Again third iteration M3 equal to M2 minus alpha into dou j by dou m at again batch 1, like this, batch 1, batch 2, batch 1, batch 2 and so on. So based on how many batches should I do, depending on the data number of data points, you can divide them into batches. I have taken only 2 batches here, 1, 2, 3, 4 as one batch and 5, 6 as another batch. So depending on my problem, depending on my number of data points, I can divide them into batches. So in the first iteration, I will use batch 1 data points only. To calculate dou j by dou m, I will use only batch B1 points. In the second iteration, I will be using B2 points. In the third iteration, again I will be using B1 points, right? So these are the 3 different types of gradient descent. When you are calculating the values, when you are calculating the slope value or the derivative value, we are choosing different data points. In batch gradient descent, I will choose all the data points. In stochastic, I will use only one data point each time. First one, then second one, then third one, again first one, second one, third one, again first one, second one, third one and so on. Whereas in batch, I divide them into batches and I show the stochasticness here. So batch 1 first, then batch 2, again batch 1, again batch 2 and so on, right. So this is about gradient descent, different types of gradient descent techniques, right. So next we will try to see one small demo in Python programming, because actually this is numerically we are trying to, with pen and paper we are trying to solve it. We can do the same thing better using Python programming as well. So let us try to see that, try to understand the programming aspect of this gradient descent, because it is very easy there. We need not do all these calculations. Automatically you give the data points, you give the data set to that, you give the learning rate, you give the initial values, it will automatically find out the best values for us, right. It will repeat until some point and it will stop. We will see the practical demo of that in some time, right.